She's downstairs.
Before I start, I'm going to do a little activity in the beginning of the lecture. I want to pass this hat around. It's my hat. And there are little pieces of paper here. Each has a number written on it from 1 to 6. So please, each person, maybe just the first two rows are enough. Pick out a number, pick out a little piece of paper, and don't show it to anybody. It's your private signal. Okay? Okay. So what I'm going to talk about, I'm not going to talk about the voter model. I apologize. I'm sorry. I know it was on the list of topics, but I had to cut out something. So the models I'm going to talk about are also about people learning from each other and updating their opinions or choosing actions. They're going to be different than Ben's models in two important ways. One way is that people's actions are going to be discrete. In fact, they're always going to be just one of two different things, right? So Ben had this continuum or a real number or even some element of a vector space. Here there are only going to be two options, say 0 or 1. And the other one is that people here are going to be amazing Bayesian rational computing machines that always do the best thing they can do. And I'll explain formally what I mean by that when the time comes. And I'm going to talk about, there'll be two parts of the lecture. The first part is going to be about sequential models, where you have a group of people and each one of them has, they go in some order, and each time one of them in turn chooses some action, and then the thing is over. There'll be a repeated models section where everybody takes an action again and again and again, which is actually more like Ben's models. So let me start with a motivating example. Imagine that there's a new restaurant, and you have to decide whether you want to eat out in this restaurant or you want to stay home. Okay, so each person, and you only make this decision once. Let's just imagine you only make this decision once. And the restaurant gives out free samples. So you can go, have a free sample, and then decide whether you want to go or not. And also, you see what people before you have decided. So you see people going, taking a free sample, and then deciding whether to go in or go and eat at home. Then it's your turn. You can have a free sample if you want, and then decide, or you can just decide without the sample. Okay. And the way it works is this: a restaurant either has a good chef or a bad chef. And actually, making a falafel or something is not that difficult, but there's some randomness in it. So anybody, whether they're good or not, when they make a falafel, it comes out either good or bad. And say on a scale from 1 to 6, it comes with even probability 1 to 6. So this is just a fair die toss. That's what happens when anybody makes a falafel. The difference between a good chef and a bad chef is that the good chef, if the falafel is not a perfect 6, he'll make another one for you and give you the better of the two. Okay? So you can imagine it. So now I can reveal what's behind board number 1. Thank you. Thanks. So bad chef, these are the probabilities of each rating of the falafel. They're just all 6 out of 36. The good chef, this is just the distribution of the maximum of two fair die tosses. There's only 1 out of 36 chance that it's a 1, right, if both of them came out a 1. And so on. It's easy to calculate. 1 out of 36, 3, 5, 7, 9, and 11. Okay? So the experiment I want to do is exactly this. Each one of these little pieces of paper has a number from 1 to 6, and either they were all picked from this distribution or were all picked from this distribution. I'm not going to tell you. And each one of you in turn, so we'll start here and go like that, has to decide and is going to declare to everybody whether they're eating in or going out. Okay? So imagine that this is your sample that you ate. You figure out where it is on a scale from 1 to 6. And then you decide whether you want to go and spend money at this restaurant. And let's just assume that, to be formal, but here you can sort of do what you want, if you think that the probability that the chef is good is higher than a half, so if you think it's more likely that the chef is good than the chef is bad, then you decide to eat out. Otherwise, you stay in. Okay? I'll explain later. Mystery column. Okay, and of course you know what other people before you did, so that should give you some extra information, right? If everybody's going to this restaurant, maybe that should tell you you should go. If everybody's not going, that should also tell you something. Please don't try and actually calculate these probabilities in your head. The assumption here is that somehow magically you do that without having to, right? But so let's start. So are the rules clear? Everybody you don't say how good it is. You just say whether you decide to eat in or go out. Okay? So let's start. Eat in, yes.
Eat out.
Out.
To the restaurant.
To the restaurant. Okay. Maybe you should say home and restaurant. Let's do it this way to make the signal stronger. Yeah.
Home.
Home.
Restaurant. Shall we take into account the previous answers?
Oh yeah, by all means. By all means.
Restaurant.
Restaurant. Home.
Restaurant.
Yeah?
Home.
Okay, so as you'll see, this experiment proves that this model doesn't describe how people actually behave. But I guess we knew that already, so it's not that informative. Okay, so this model was introduced by Banerjee and at the same time by Hirschleifer, Bictondani, and Welch. And then there was a very important contribution by Smith and Sorensen that I'll mention in the end. So let me write down formally what the model is. Sorry?
Was it good or bad?
It was actually bad.
So it did behave correctly because the cascade broke.
Well, but actually, if you do the calculations, there should have been a bad cascade very early on that would never break. Okay, so here's the model. We're going to have a state of nature, theta, which is either 0 or 1. So this would be good restaurant or bad restaurant. And we're going to have a set of players n, which we'll just take to be we'll enumerate them by the natural numbers. They each have to choose an action. So actions xn, which are again in 0, 1. And the utility, when the state of nature is theta, and you choose some action x, is equal to 1 if x is equal to theta, and 0 if x is different than theta. So you're sort of trying to guess what the state of nature is and match that with your action. Okay, so yes?
I don't understand how it can be a state of nature. It's not something objective that we can say that it is a good restaurant.
No. Either the chef is good and makes you another falafel if the first one's not perfect, or he's not. That's it. And that's chosen once at the beginning at random, and that's what it is.
It is a matter of taste.
So it's a matter of taste, and here we're going to assume that everybody has the same taste. In this paper of Smith and Sorensen, they actually look at cases where different people have different tastes, and you have some very interesting things going on. But already in this very simple model, there's some interesting phenomena. Okay. Okay, and then we're going to have people taking actions. First, person 1, then 2, then 3, and so on. Each one of them gets a private signal. So Sn is a private signal. And it's IID, their IID, conditioned on theta. And you can just keep this example in mind, right? If theta is 0, then they all come from this distribution, independent. And if it's good, then they all come from this distribution, independently. So the information available to person I, to person n, we'll call it In. Well, that's all the actions of the people that came before her, x1 up to xn minus 1, and also the private signal Sn. Okay? And now I have to, person n has to make his or her decision. So the utility of person n is just this, it's the same thing for everybody, so everybody has the same taste. So what is person n going to do? So now we're assuming that people are these perfect Bayesian machines. So they're going to calculate their expected utility if they take action 1, if they take action 2. So the expectation of un conditioned on what person n knows, and if they choose xn equals 1, well, if you do the math, that's just the probability that theta equals 1 conditioned on what they know. And likewise, equals 0, sorry. That's the probability that theta equals 0 conditioned on what they know. So if they are expectation maximizers, they're going to choose either action 1 or action 0, depends which of these two is larger, which means that xn is the arg max x in 0, 1 of the probability that theta equals to x conditioned on in. Now I'm cheating a little bit here because I write equals. What happens if these probabilities are both the same? So I'm going to ignore that option in this talk. It's sort of an annoyance that you have to deal with when you want to write down a paper. Let's just assume this never happens. Okay? But really all the results still hold no matter what you do. So just assume that each person does something and everything still holds. Okay. So is this clear? There's something that I maybe should have added here. There's some probability that theta is equal to 1. And in general, we're going to assume that this is, should assume that, this is strictly between 0 and 1. Just to make it simple for this talk, we're going to assume that this is just equal to 1/2. And everybody has this common prior on theta, okay? And everybody also has a common prior on the distribution of signals and so on. So this is, okay, any questions about this model? So this, now we have a well-defined model, and in any equilibrium, people will do this, minus this indifference business. And I'm assuming people are doing this equilibrium here. Any questions about this? Yeah? For these results, yes, I think so. Yeah. Anything else? Okay. So what we're going to be interested is Qn, which is the probability that xn is different than theta. That's the probability that person n got it wrong. And in particular, we're going to be interested in the question of whether Qn tends to 0. As we go further and further down the line, do people get it correct with higher and higher probability? Do they make a mistake with lower and lower probability? So one thing to observe is this. Say if instead of this, we just show to the nth person all the private signal of the people who came before them. Okay? So imagine somebody who knows the private signal of the first n players. And you can ask, what is the probability that that person gets it wrong? And the answer is sort of a classical question in Bayesian hypothesis testing. You're just doing n experiments. And the question is, what is the probability that you guess the correct answer after doing n experiments? And the answer is, so if you know n private signals, then the probability of a mistake is e to the minus some constant r, which amazingly you can calculate. There's a very nice expression for it. Depends on what the distribution of private signals are. E to the minus r times n. plus some little o of n. So the probability of the mistake decays exponentially fast if everybody were to observe all the private signals of people before them. So in particular, it would go to 0. The question here is not even whether it decays exponentially fast. Does it even go to 0? Okay? And we're going to say that when Qn goes to 0, we're going to call this phenomenon asymptotic learning. So we have asymptotic learning in this model or in some model if the probability that people make mistakes go to 0. Now, I mean, from an economist's point of view, this is an asymptotic statement. So it's about the gazillionth person, or not even that, past that. So you could argue that this is not really an interesting question to ask from an economics perspective. Yes, I don't know how to answer that, but I like this question anyway. Yeah. Well, if you know S1 up to Sn. If you, pardon me? If you know n signals. Okay, so
that is different from the experiment that we just did in the class.
this is different.
Yeah, the setting that everyone knows the private signals of previous people.
That's different from what we did in class. What we did in class is this, where what I know is just the actions of the people who came before me, and I don't and my own signal. That's it. Okay? So that's where the inefficiency is going to come from. And in fact, we're not going to have asymptotic learning. Okay? So let's try and see what's going on here. One way of looking at how people make decisions is that they calculate this probability, whether the theta equals 1, and they check whether it's higher or lower than 1/2, and decide according to that. I want to do the same calculation but slightly differently. I want to look at the likelihood ratio. So I'm going to define the likelihood ratio of player n as just the ratio of these two things. So that's the probability that theta equals 1 conditioned on in divided by the probability that theta equals 0 conditioned on in. And this is just easier to work with algebraically. Now we can say that a person will choose action 1 if this is above 1, and we'll choose action 0 if this is below 1. Right? Now we can apply Bayes' law. So when we apply Bayes' law, we get to switch this and this. And then we have to multiply by the probability that theta equals 1 here, and by the probability that theta equals 0 here, and divide by the probability of in. And all these things cancel because we chose this half-half prior. And really what we have left is the probability of in conditioned on theta equals 1 divided by the probability of in conditioned on theta equals 0. Okay, so this, I don't want to do the details, but this uses the fact that we chose a half-half prior to cancel that constant term that we would have had to carry along. Okay, so let's write this out. In, which I erased, this is what person n knows. So it's the actions of the people who came before them, and also their own signal. Now, condition on theta equals 1, my signal is independent of everybody else's signal, which means that it's independent of their actions, because they haven't even seen my signal yet, right? So their actions are independent of my signal. So because we're conditioning on theta, we can separate that to a product. These things are going to be independent, so we can write this as the probability of x1 up to xn minus 1 conditioned on theta equals 1 times the probability of Sn conditioned on theta equals 1, and we're going to have the same thing at the bottom. Okay, so let me try and make sense of this. And one way to make sense of this is to introduce a new character into the story. And this is going to be an outside observer who has no signal of her own and doesn't have to make any decisions. She just gets to observe the decisions made by people. So we have person 1, person 2, and so on. And then we have this outside observer O, who's just looking at what's going on here. And then you can, after some amount of time, you can go to this outside observer O and ask her, what do you think? What is the probability that theta is 1? What is the probability that theta is 0? What is the likelihood ratio? And what is this person going to tell you? Just this first term here. So I'm going to define the nth likelihood ratio of the outside observer as exactly this term. And this term, so that you can interpret as, this you can interpret as the likelihood ratio when you only look at your own signal, right? This is before you've observed anybody else. You just look at your own signal and you ask yourself, what's my likelihood? So we'll call that the private, so this is sometimes called the public belief or the public likelihood ratio. This will be the private or the signal likelihood ratio. So this will be ln s, which is what is over there, and that's just that. And it's important to note these are random. They actually depend on what the signal was. They depend on what the actions were. And then we have this very important formula that ln is just the product of ln O times ln S. And here I went ahead and calculated ln S. So you can see so this is the ratio of the probability that theta equals 1 to the probability that theta equals 0, just based on my own signal. If the signal is 1, it's 1 over 6, 3 over 6, 5 over 6. These are all lower than 1. So if I got 1, 2, or 3, and that's all the information I had, I should decide to stay home. And here, 6 over 7, 9 over 7, and 7 over 6, 9 over 6, and 11 over 6 are greater than 1. So here, if I just got any of these signals, I would decide to go out. Okay? So that's that LNS. Okay? Now, this LNS is very nice to look at because it converges. And this just follows from the martingale convergence theorem. I won't show the actual proof, but here's the claim. ln O converges to some L infinity O. This outside observer, she sees the sequence of actions. Her likelihood ratio will converge to something. It converges to 0. It could converge maybe to 0. Maybe it could converge to infinity. Maybe it converges to some number. But we're guaranteed that it actually converges. Okay? Here's another thing that we can say about this LNO. I'm the outside observer. And I see Elchanan making a choice, and then Eric making a choice, and so on and so on. So I see Ben making a choice. And now somebody asks me, what is your choice? So say Ben did 1. What would I say? I have all sorts of things here that ended with 1, hint, hint. What would I say? Any guesses? 1. Okay. Why would I say 1? Exactly. Ben has more information than me. He sees everything that I see, plus he has his own private signal. So if I had to make a choice, I'd say, yeah, whatever he says. He's smarter than I am. So here's another claim. So Ln is based on the, this should be the first n minus 1 signals. It's based on the first n minus 1 signals. So if xn minus 1 is equal to 1, then ln O is greater than 1. And if it's equal to 0, then it's less than 1. Okay? So now let's see what's actually going to happen here. And I want to draw a graph. So this is the nth person taking their action. And this is going to be ln O, the likelihood ratio of this outside observer. It's positive. And it starts out from 1. And then a person takes an action, so it's going to maybe go up to something, it gets updated, it goes down to something, and so on and so on. We have some graph here. Now, when it's time for person n to act, they take this ln and they multiply it by this number that comes from their own signal. Okay? Now, if you notice here, the smallest this number can be is 1/6, and the highest is 11/6. Which means that if ln O at some point goes above 6, then what? Sorry? Yeah, well, what's going to happen is, having observed everybody who came before me, the likelihood ratio of the observer, which is mine before I looked at my signal, is above 6. Which means even if I get the worst possible signal, which is 1/6, I won't go down below 1. So no matter what signal I'm going to get, I'm not going to change my mind. I'm going to go to the restaurant. I'm going to choose 1. Okay? So here, because we have a finite possible outcomes of this signal, or what's more important is that these are bounded, there's going to be some threshold so that if I go above that threshold, I'm going to, if once ln O goes above that threshold, the nth person is not even going to look at their private signal. They're just going to take the same action. Now, if the person before me, let's say that ln O went above this 6, and it's not my turn yet, it's the person before me, but person before me hasn't made a choice yet, but already ln O is above 6. I know that this person is not even going to look at their private signal. I know what they're going to do. It doesn't matter what their private signal is. So when they do that, I don't learn anything, right? So then ln O is just going to stay the same, and the same, and the same, and everybody will just do the same thing from that point on. And there's going to be another threshold down here with the same thing. If we ever go down below that, by the same argument, it's going to be the same. And the threshold here is 6/11. Okay? Yeah?
But that means that there is a positive probability of mistake. So suppose the first people
Yes.
receive the wrong signal.
Okay, so you...
Above 6, it has a positive probability.
Okay, so I'm glad I didn't tell any jokes because you would have ruined my punchline. You ruined my punchline, that's what I'm saying. Yes, no, I'm not blaming you, I'm sorry, but yes, that is the punchline of this story. There's positive probability. Imagine that the first whatever number of people got the wrong signal. That happens with some probability. It will go, okay, say that the truth is that the cook is fabulous, but it just so happened that the first 10 samples that the cook made were bad, and it goes down below this threshold. That's it, it's over. You saw a few people not going to the restaurant, you don't even need to look at the sample. You're just not going to go. Even if the sample is very good, it's not going to change your mind. You're just not going to look at your sample and you're not going to go. And this happens with positive probability. Also in the other direction, it happens with positive probability. And that's it. There's a positive probability that everybody gets it wrong, and therefore this probability of mistake doesn't go to 0. In fact, it's going to have a limit still, but it's going to be something non-zero, and you don't have asymptotic learning. Okay. And in fact, in this model, I won't carry out the calculation. It's enough that one person decides not. So what should have happened here? The first person, if Elchanan would have said, "I'm staying in," everybody else should have just not looked. See, so I won't take the time to do the calculation, but one could. It's very easy. Any questions about this? Okay.
So why is that true right now? I'm staying in, suppose Eric would have buried that signal.
Okay, so let's do the calculation. If you're staying in,
And suppose Eric brought the signal 1.
So let's calculate ln L2O. So the likelihood ratio, when the first person decided to say, decided to not go, right? So this is the probability
Sorry, you're talking about the situation where the first person decided
not to go. Let's do the calculation. It'll take 2 minutes. So the probability that x1 is equal to 0, condition on theta equals to 1, divided by the probability that x1 is equal to 0, condition on theta equals 2. Okay, so if theta equals 1, so if the cook is good, what is the probability that you won't go? Well, you wouldn't go if you got a 1, 2, or a 3. So that would be 9, I think, out of 36. Here it would be 18 out of 36, right? So this would be 1/2. Now the next person, they're multiplying this 1/2, but by whatever they got from their own signal. But that's never going to be more than 1, because the most they can multiply it is by 11/6, which is less than 2. Okay? So I don't know exactly, this is not exactly what happened. I was hoping that you would say, no, I should have rigged it somehow. But I think even if the first person says eat out and the second person, I did this calculation actually, the first person says eat out and go to the restaurant, and the second person says stay home, everybody should just stay home after that. So it turns out in this case. Okay. So now I want to talk about what happens when we introduce networks. And this is the paper by Darona Semoglu, Manzur Dale, Ilan Lobel, and Asu Ozdaglar. By the way, I should have said before, everything that I'm talking about is splendidly covered in this survey by Golub and Sadler. So I encourage you to look over there, and of course, many more things.
What did Smith and Swan?
Oh, good point. Okay, I forgot to mention that. So imagine that I had private signals that weren't bounded. So maybe I have a continuum, or it's enough just to have infinitely many possible signal realizations. And furthermore, they have the property that they can go arbitrarily close to 0 and arbitrarily close to infinity. Here, they can be arbitrarily big. Well, what happens then, this ln0, ln0, this observer's likelihood ratio, still has to converge by the same martingale convergence argument. But it can't converge to anything finite. Because you're always going to have, with some probability, somebody who's going to have a very strong signal who would overturn that. Okay, so I don't want to go through all the details. Okay, I'll go through some of the details. Imagine for a second that it does converge to something finite. And converges to this. This is some number, say 7. Well, eventually, because these signals are unbounded, you're going to have somebody who's going to say, oh, I disagree, and will take the other action. Now, remember I said once anybody takes the opposite action, the observer updates their likelihood ratio to match that. So if anybody takes action 0, that's going to drop below 1. Okay? And then once it drops below 1, okay, so it can't just converge to some number. Okay, so if you assume by contradiction that it converges to some finite number, that's impossible because eventually it'll drop back to the other side of 1. And the same argument holds on the other side. So it has to converge either to infinity or to 0. And it turns out that when it converges to infinity or to 0, people also take the correct action eventually. Okay, and something stronger is going to happen here. It's not just that the probability that people take the correct action is going to go to 1, but from some point on, everybody will take the correct action. Because if this converges to infinity, then from some point on, maybe in the beginning it crosses 1 a few times, but from some point on it'll always be above 1, and then everybody will take the action 1. And if this goes to infinity, that also has to be the correct action, because in a Bayesian world, you cannot be 100% certain about the wrong thing, and here your degree of certainty goes to 1. Okay, so I'm not filling in any of the details, but okay. So that's Smith and Sorensen. And they have more interesting results, or for example, what happens when people have different preferences. Okay, so let me talk about this paper. And what they do here, they introduce a social network. Was there a question? Yeah.
Yes, and I think this model, the formation of cascades strongly depend on you have belief that the people are rational.
Yes.
Is there any paper try to relax the assumption that
Probably. Do you know, Ben, or somebody knows? I'm
Right. Basic logic is robust, though, right? Because if there's some probability that, maybe some people are, I guess there's a lot, right? The sacrificial lambs is the standard term, but if there are people who just, for example, follow their signal and don't do any of this thinking about what others are up to, they're basically a force against cascades, right? 'Cause
Yeah.
They'll sort of reset it, and then people, if there's been a bad cascade, you get new information from these people. I think that's the closest.
Right. Yeah. I don't know more than that. Okay, so let's talk about social networks. Yeah.
There's something I don't understand.
Yeah.
about the last thing you said.
Yep.
You said there's a point after which everyone will take the correct decision.
Yes.
But if signals are unbounded, and I get a very extreme but also wrong signal, why doesn't that outweigh?
Well, okay, so what's going to happen is that this LNO, say the truth is that the correct action is 1, so then this LNO will actually go to infinity. Now, when you're further and further down the line, you need a stronger and stronger signal to overturn it. So there's a bit of a race condition here. Does this grow faster than the tail of the signals?
That's what I don't say.
And just because this has to converge to infinity, their answer is you will only have a finite number of opinion switches. Because this has to converge. So the probability that theta is equal to 1, condition on x1 up to xn, this is a martingale. It's a bounded martingale that converges, which means that this also converges. It can converge to something finite. It has to converge either to infinity or to 0. So that's it.
Eric understood, but one of the
Okay, so
consequences of this question is now I don't understand.
so let's call this Bn.
At any point, you can have a signal that, since you're unbounded, that at any point of time, this Ln is very high, that was a finite value,
Yeah.
and you could have a signal that would outweigh it.
Right. So imagine, well, imagine that at time n, the probability that you get a signal that makes you overturn goes down with time because this goes up and up. Imagine that at time n, the probability that you get an overturning signal is 1 over 2 to the n. Then the total, imagine that these are independent, the total number of times that this will happen will be finite. Okay? And it turns out that no matter, it's always going to work out. Okay. Okay, so let's look at the social network setup.
You're making a statement which is true with probability 1.
Yes,
But there could be a probability 0.
Yes,
It's possible that we could have an infinite
absolutely,
number at just,
absolutely.
probability 0.
Yes. I hereby append almost surely to all of my sentences. Okay. So now let's talk about networks. So we're going to have some network of connections, and this is the same set of players we had before, 1, 2, 3, 4, 5, and so on. And they each they act in turn just before. This guy goes first, then she goes, and he goes, and so on. But this time they don't observe the actions of everybody who came before them. They just observe some subset. So imagine that person 2, when they act, they'll observe the action of person 1. They're also connected to 3, but that doesn't matter because 3 hasn't done anything yet. So person 2 will just observe the action of person 1. Person 3 will just observe person 2. Person 4 will observe all 3 who came before her, and so on. In general, we're going to have some Bn, sorry for using that before, that wasn't planned, which is a subset of 1 up to n minus 1. And these are the people that person n observes. And we're going to allow this to be a random variable too. And these are going to be independent random variables, independent of each other and of the private signals and the state of the world and so on. So these are independent random variables. What we had before is a special case of this when Bn is just almost surely equal to 1 to n minus 1. Okay? Which means that the information available to person n in this case is going to be, again, for private signal, but also all the xm's where m is in Bn. Okay? And again, we're interested in asking whether Qn, which is the probability that xn is different than theta, whether this goes to 0. And let's talk about bounded signals. So have this example in mind. It turns out that this now depends on your choice of Bn. Well, we know that if Bn is just everything, then this doesn't go to 0. But I think maybe the main result of their paper is an example of some family of Bn's where this does go to 0, where you do have asymptotic learning. And let me tell you what maybe the simplest example is. So let Bn equal the empty set with probability 1 over n, and Bn is equal to everybody who came before with probability the rest of it, 1 minus 1 over n. So the nth person with probability 1 over n doesn't observe anybody, which means that they just go by their own private signal. Otherwise, they observe everybody before them, and they sort of do the same calculation we did before. Now, here's a very important thing. When you observe somebody taking an action, you don't know what the realization of their Bn is. Okay? So I don't know if any of the people before me, whether or not they observed everybody who came before them or not. Pardon me? Right, so you could learn from what they do something about the network that they have. Okay?
And this relates to the rationality question, because another way of seeing it is this guy who observes nobody, it may be that he does, but for some reason he doesn't know what to do with that information.
Right.
He just uses his own signal.
Right. So this could subsume some non-rational model, right? Yeah. Okay, so is the setup clear here? I didn't write exactly what the action is, but you calculate your likelihood ratio. If it's above 1, take action 1. If it's below 1, you take action 0. Okay, is this clear? Okay, so let me give a proof sketch of their theorem, which says that in this case, Qn goes to 0. And what we're going to do, we're going to keep the same LNO that we had before. So LNO is going to be just like before, this likelihood ratio of what everybody did up to person n minus 1. In this case, however, we don't have the equation. So in general, Ln is not equal to LNO times LNS. If you remember, LNS is what you get from just seeing your own private signal, these numbers. In general, this is not true. For example, if you didn't observe anybody, your Ln is just equal to your LNS. But this will be true when Bn is everything. Okay? by the same calculation that we had before. Now, LNO is still a martingale. So it's not a martingale, sorry, but by the martingale convergence theorem, it converges. And let's assume by contradiction that it converges not to 0, not to infinity. So, assume by contradiction that lim LNO is finite and is not 0. And let's just say that it's above 1. So we can do the other case, but we won't. So let's just look at the case that it converges to something that's above 1. Well, what's going to happen is, if I'm the outside observer, my opinion converges, and it converges to something that's above 1. Okay? Now, if somebody sees everybody who came before me, from some point on, they'll also take the action 1. Because they're also up here. So when I see somebody taking the action 0, I learn that they're one of these people who don't have their own signal. And when I see somebody do that, I have to update my ln plus 1 by some factor which doesn't depend on n. It's going to jump by some constant number, which means that it can't converge. And this is going to happen infinitely many times. Why is this going to happen infinitely many times? Because the sum of 1 over n converges. The expected number of people who don't observe any signal, who don't observe other people's action but just go by their own signal, is infinity, because we chose here 1 over n as opposed to, say, 1 over n squared. Okay? So with probability 1, we're going to have infinitely many people who just act by their own signal. So it's impossible that this LNO converges to something finite, which means that it has to converge to either infinity or 0, which means that those people who do see everybody, they will also know the answer with probability that goes to 1. So the limit of the probability that xn is different than theta, conditioned on bn being everything, is going to be 0. Those people who do see everything, they will learn, which means that qn, which is the probability that xn is different than theta, well, I can condition once on bn being this, and that will go to 0. So let's call this thing qn hat. So it'll be qn hat times the probability of this thing, which is n minus 1 over n, plus conditioning on the other thing, probability that xn is different than theta, condition on bn being the empty set, times 1 over n. Now qn hat goes to 0, and this goes to 0 because this is between 0 and 1, and this is 1 over n. So we get that, that this goes to 0. Okay? So I cheated here a little bit in this proof, but I think that's the idea of what's going on.
So in that last step, you used the fact that you've already shown that it converges?
That LNO converges.
Yeah.
Yeah.
You used that in the last line.
I use that here. It converges, and not only that, it converges to either 0 or infinity, which is what this says.
Okay. And then the next line does what?
The next line writes qn, which is the probability of mistake. I write this, I condition once on person n seeing everybody and once on person n seeing nobody. These are these two terms. This is the probability of mistake conditioned on person n seeing everybody, which is something, qn bar, which goes to 0. this is conditioned on the other thing, but this term goes to 0 because of the 1 over n. Any questions?
Where do you cheat? I didn't see it.
I'd rather not reveal my... magician never reveals. There's some subtleties here because when somebody here takes an action 0... Okay, I address...
Okay.
Okay. But I'm glad that the trick worked.
But the difference here with Smith and Sorensen is even though you, asymptotically, the mistake probability is going to 0, you continue to have mistakes because there are always these people who don't see anything.
Yes. And I think an interesting question which they don't address in this paper is whether it's possible to have finite net, with bounded signals, convergence in the other sense. So convergence, pointwise convergence, and they don't really yes?
So it seems like this whole thing is dependent upon the probability of observing nothing going at the rate of, decaying at the rate of 1 over. Are you intuitive on why that would ever happen? I mean, obviously it's a point model, but that seems a little...
Yeah. I mean, I think what's the nice thing about this is it's an example where for some social network, you do have learning despite the fact that signals are bounded. And this is one example of a big family of networks for which you can get it. You know, you can imagine that I can play around with a lot of things here and still get it. This is sort of the simplest example where you can explain why it works. But they give some more general family where the same thing happens.
But the interesting thing is that worse information promotes social learning.
Right. Yeah. People here observe less and somehow they...
So there's a negative externality, you're better informed.
Right.
Yeah. Okay, so... sorry, yeah?
But he says worse information is promotes social learning, but the amount of worse information has to be declining over time. Right?
It has to be declined. This has to go to 0, but the sum has to go to infinity to make this work.
So the probability of observing worse information in some sense has to be declining over time.
Yes. But this is strictly dominated, right? So there's strictly less information here than before. Okay, so I have until 1, right? So there's another half hour. Okay, so what I want to talk now is about repeated models. And I'll mostly talk about the work of Mosul Sly and myself. So this is a slightly different setup. It's the same informational setup. So we're going to have theta and Sn as before. Well, we might need slightly different Sn. I'm going to need these to be non-atomic. And by non-atomic, I mean when I show somebody their private signal and they form their own belief or likelihood ratio, I want any particular value of that belief to happen with probability 0. So the way to do that, you can imagine that this chef, instead of making a falafel that goes between 1 and 6, the integers 1 and 6, they make a falafel that's uniformly distributed on the reals between 1 and 6. And then if they're bad, they do that once. If they're good, they take the maximum of 2 things from this distribution. Okay, so that would be an example of that. We don't need to have unbounded likelihood ratios, which will be interesting. But theta is again either 0 and 1, and these SNs are conditionally IID on theta. So everybody starts out with some private signal. Now we have discrete time periods. So time will go 1, 2, 3, and so on. And each person takes an action at each time period. So the actions are still either 0 or 1. But I have to make one every day. So here's a slightly different story than the restaurant story. The story is this. You have a baby. I don't know to how many people this is relevant here, but but it's relevant to me. And you have to decide whether to put them to sleep on their stomach or on their back. Okay? And in the beginning of time, so when your baby is born, you get some information about which is better. This is very noisy information because really the experts know nothing. But in the beginning of time, each member of society gets some information. That's it. There's no more information coming into society. Now, every day, you decide whether to put your baby to sleep on their back, on their stomach, and as one does, you post to all your friends on Facebook what you did. Okay? And see what they did. Okay? So the information available to person N at time t will be their one private signal that they got in the beginning, and then x m tau, where tau is less than t, so from the previous time periods, and m is in this b of n, which like before is my set of neighbors. So b of n in this case will be a fixed, it's not going to be random, just a fixed finite subset of the set of players. Okay? Now, every day I want to do the right thing by my baby. And as before, the utility of person n at time t for a given theta and given their action, x and t, will be the indicator that theta is equal to this x. So just like before. And people's total utility would be a discounted sum. Whoa. So we have some common discount factor lambda, and the utility of person n for a given theta and a given sequence of actions will be 1 minus lambda, the sum t equals 1 to infinity. Maybe it should go from 1 lambda to t minus 1 times this unt. Okay? So this defines a game. My strategy is, at every point in time, what do I do given all the information available to me? And you can ask what happens in equilibria of this game. This game might be a little hard to think about, so you can imagine what happens when we take lambda to 0 and people are myopic, so they don't care about what happens in the future, and they just try to maximize this at every point in time. And you already get pretty interesting results there. Okay, so is this game clear? Is this setup clear here? Okay. So here's one theorem. Sorry? The utility, it's just 1 if theta is equal to x and t and 0 otherwise. Was this your question or? Yeah? Okay.
Sorry.
Yeah.
Do they get the day off, so the end of each period or
No.
the end of the last period?
You put your baby to sleep either this way or that. We assume that he never dies. Your utility you get in his longevity. He lives to be 80 instead of 90 or the other way around. Okay. I gave this talk and there's a great economist called Najib Ali. He's in Penn State and he told me, I have a better example for you. Every Saturday you decide whether to go to synagogue A or synagogue B and you get your reward in the afterlife. You don't get any indication of which is the true belief. Okay. Oh, so I should mention, just like with Ben, we're going to assume that the social network is strongly connected okay, so there's a path from every person to every person, otherwise you can't really expect much to happen. So the first theorem is the following. There exists a random variable x infinity such that lim x and t is equal to x infinity for all n. Okay, this theorem is not true. There's some subtleties here, but I want to skip them. So what? So I apologize. There's a lot of technicalities there, and I want to give the main idea. So this theorem is not true as written, but let's just imagine it is true, and I want to parse what it says. It says everybody converges to some action. So every day I decide 0, 1, 1, 0, 0, 1. Eventually I get fixated on either 1 or 0. And furthermore, this thing that we all get fixated to is this thing, so each one of us gets fixated to something, but these are all the same. It's still random, okay? With some probability we all eventually do this action, with some probability we all do that action, but we all eventually converge to the same action. So we have agreement in the end. And this mostly follows from the really beautiful paper of Rosenberg, Solon, and VA, who show that, so this is in the spirit really from, it starts from Aumann's agreeing to disagree, and then there's Giannakopoulos and Palmer-Chakis and McKelvey and Page and Gale and Kariv, and I think it culminates with this literature. And what this literature shows is that rational agents cannot agree to disagree. If you keep on exchanging information and observing each other, and you need the social network to be strongly connected for this, eventually you'll have to agree. Now, in all these papers, there's one caveat, which is you have to agree unless you're indifferent. Maybe I'm indifferent and I take action 0, or you're indifferent and you take action 1. So we take different actions, but we don't really disagree. So to get rid of that, we need these non-atomic private signals so that we don't get stuck in because of indifference. And it turns out that you can actually get stuck because of indifference. This is not just a matter of not being able to prove. You can actually get stuck because of this indifference. At least in the myopic case, I can show that. So I want to assume these non-atomic private signals, which means that everybody eventually converges to the same action. Okay, we all get our private signals in the beginning, once and for all. We start acting, we observe each other's actions, and eventually we all take the same action. Now, if this is an infinite graph, then it could be that different people converge later and later, and so on. But everybody converges to the same thing. Okay, is this clear? Good. So now the question is this thing that we converge to, is it the correct thing? So we can ask, what is the probability that xn is equal to theta? So if we have a graph with 100 people, presumably if they all get the wrong signal in the beginning, then they'll all converge to the wrong thing in any equilibrium. I think that's a reasonable, I don't know how to prove that, but definitely for the myopic case this is true. So you can't hope for this to be 1, at least not on a finite graph. But what you can hope is if I take larger and larger graphs, so there's more and more signals between society, the probability that people get it right goes to 1. Or you can hope that if I have an infinite graph, then the probability is 1. And it turns out, well, the easier case to analyze turns out to be the infinite graphs. So I'll just talk about them. The proof for finite graphs is really reducing it to the proof of infinite graphs by looking at limits of things. But for infinite graphs, it turns out that for some graphs, this probability is 1, and for some graphs, it's not 1. So in some graphs, information gets aggregated, and everybody does the correct thing eventually. And on some graphs, with some probability, things go wrong, and all this wonderful information that everybody has gets lost, and you do the wrong thing eventually. Yeah? Well, you sort of have to assume that the structure is common knowledge. Otherwise, it's hard to say what the equilibrium concept here is. So to have a rational model, really, I don't see how you cannot have common knowledge of the graph structure. You can start talking about distributions on graphs, and have common then knowledge of what this distribution is and the common priors and so on. But I don't think that would add, okay, that's something to look at. I think the result will somehow stay similar. Okay?
I guess the most general case would be people have arbitrary different beliefs over the graph structure and you look at rationalizability or something.
Yeah. If people have different beliefs, then these agreement theorems stop working. And then you won't have learning. It'll be very difficult to generate a graph, a setting where this will still work, I think. Yeah. Any more? So let me start by giving, yeah?
Can I see these results as a generalization of a convergence theorem?
Sure.
He has similar ideas that the more.
Yeah, so sometimes sometimes the more people you add, the higher the probability that you get it right. But for sometimes, no. Okay? So if you have a Condorcet jury with Napoleon calling the shots, then it's not going to happen that you add more and more people to the jury. Yeah?
These are some classification of like graph structures.
Oh, yeah. Not complete, but there's examples of graphs where this is not 0, and there's sufficient conditions for this to be 1. So I'll show both. So let's start with graphs where things go wrong. And you'll understand very quickly why things go wrong. And just for this example, let's imagine that agents are myopic. So we're taking lambda to be 0, or the limit as lambda goes to 0, and I just try to do whatever I think is more likely to be true at each iteration. Yeah?
Maybe I'm confused.
Yeah.
Can't you get an example where things go wrong by simply extending the first example to a situation where each time you pick a restaurant in a way?
The first example is not strongly connected. So I want a strongly connected example. Otherwise, it's not even true that everybody does the same thing eventually. Necessarily. Maybe in some examples. So the graphs that we had in the sequential model are not strongly connected. There isn't a path from every person to every person. All the edges are directed in one direction. Right? So if I'm behind you in line, I observe you, but you don't observe me. But in some sense, this is it. If we choose this every day, and you observe some people and they observe you, but it turns out that the proof requires different techniques here. So let me give an example of a strongly connected graph where people do the wrong thing. It's going to be a royal family graph. So imagine that there's some large royal family, and they all observe each other. Okay? And then I have the peasantry. And imagine that there are infinitely many of them. Each one of them only observes their 2 next door neighbors. Each one of them observes, say, the entire royal family. Or maybe each one of them let's just say that each one of them observes the entire royal family. So this is not a strongly connected graph. To make it strongly connected, we'll add one royal who has one friend among the people. So they listen to the people's opinions. Okay? So what's going to happen here? Everybody's private signals are very weak. But if you take all of these private signals together, you get something very strong. So imagine that there are 100 royals. And at the first time step, they all just go according to their private signal. So they reveal whether their private signal pointed them this way or that way. And everybody sees this. Besides seeing this, everybody just sees their 2 next door neighbors. But imagine that all of these royals did the same thing. They all said 0. Then it really doesn't matter what my 2 neighbors said, right? I saw 100 people do 0. Even if both of my neighbors said 1 and my private signal was 1, if I put enough royals in here, that's going to trump anything that I could have. Which means that from this point on, everybody will just go according to that. Now, there are infinitely many of these, or I can think about this as a sequence of finite graphs where I add more and more people here. But there's some fixed probability that everybody will just get it wrong. And this will happen in the event that all of these get the wrong initial signal, for example. Okay? Now, the graphs that where we can prove that this actually is one, where people do the correct thing, the property that they have, we call it egalitarian graphs, or DL egalitarian graphs. And what they don't have is some group that's very strong and influential in the geometry of the graph. And this is very reminiscent, if you remember, of what Ben was saying about the Golub and Jackson paper. They're in a very different paper with different philosophy. It wasn't Bayesian, it was this naive learning, and with completely different math, you get a very similar phenomenon. If there are no important people in the network, information goes around and you have good aggregation. If there's somebody who's very important in the network, that can ruin the flow of information. So you could have a priori imagined that it would go the other way around, that having somebody aggregate information and disseminate, or having important people in the network could help the aggregation of information. Turns out that no. Important people hurt the aggregation of information. You want everybody to be the same in some sense or other. I haven't told you what our sense is, and we can argue whether this is a sense of being egalitarian or not. But somehow I think this is a common conclusion to these two models, which is interesting because they're not so related mathematically. Yeah?
It seems to me too, if lambda is close to 1, it's reasonable for a thing which is not the signal sequence of presence fields.
So say that again?
If lambda is close to 1,
Yeah?
so verification,
Yeah.
just ignore my signals in this whole thing.
So for some lambdas, it's possible that you would have learning here. But we actually have a proof that for some lambda that's not 0, you don't have learning here. So even with some non-zero lambda, this can happen. So we construct an equilibrium with non-zero lambda where this happens and people don't learn. But I don't know what to say. I don't know what to say that this will happen for any lambda. Maybe for something close enough to 1, it will be fine. Okay? Okay, so let me tell you what DL egalitarian graphs are. Like to follow the de Groot model.
No, in this model.
But what would be the rule book? You could tell them to follow the de Groot model, for example.
It's one thing you can do, yeah. But I guess with discrete actions.
Well, what you could maybe do is have them observe the important people, but not at every period or something like that. I don't know.
But is there right? So what should we think of as an efficient benchmark?
But you still want to keep rationality.
Maybe not. I just want to keep the discreteness. Oh, then they could send code right. That's right. Never mind.
I don't know exactly how to do that and keep it a rational model. And if you're not, then you do the Groot, for example. Okay, so let me tell you what DL egalitarian graphs are, and it's the following. So the size of B of n okay, so a graph G is DL egalitarian if there exists some D such that the size of Bn, the size of the number of people I observed, is less than D for all n. So there's nobody who's very, very important in the sense of observing larger and larger number of people. There's some bound on number of people you observe. And also, if there is a path, if there is an edge from I to j, which is the same as saying that j is in B of n, then there's a path from j back to I of length at most L. Okay, so this takes some digesting. Imagine for a second a symmetric graph where if there's an edge from me to you, there's an edge from you back to me. This satisfies this with L equals 1. there's an edge from E to U, there's a path back of length 1. That's just a symmetric graph or an undirected graph. This is some relaxation of the graph being undirected. So imagine that I follow Justin Bieber on Twitter, but he doesn't read my papers, and also his agent doesn't read my papers, and his agent's agent doesn't read my papers, and so on. It's a very long path from him back to me. So I don't want to allow that. I want, and this is another sense of egalitarianism, you don't have everybody, not everybody has to be close, but if somebody observes somebody, they're observed back maybe through some short path. Okay? And it turns out, and the theorem is this, on any infinite DL egalitarian graph, in any equilibrium, the probability that x infinity equals to theta is 1. Now, for those who are mathematically inclined, I just want to give a little blurb. These conditions don't come out of nowhere. You can define a topology on graphs, or on rooted graphs, which is a graph together with a distinguished vertex, or the graph from the point of view of some person. This topology is called the Benjamini-Schramm topology. And then you can, given a graph, you can look at all the rooted graphs that you can get by choosing this distinguished vertex in all these places. And this gives you a collection of rooted graphs. This collection of rooted graphs is pre-compact in this topology if and only if the graph is egalitarian. And actually, compactness is what we use in the proof. So we didn't think, oh, maybe this should be true. It turned out that you need compactness in the proof there. And this is what it translates to in geometric terms. Okay, so this is compactness or pre-compactness in the Benjamini-Schramm topology on strongly connected directed graphs.
And what is the sequence of use compactness? We have an infinite graph here, right?
Yes. Well, there's a collection of, you can get a set by looking at all the different roots that you can choose. And you can ask, is this set pre-compact? So if I take the closure of this set, do I get a compact set of graphs or not? And the answer is, if and only if the graph you start out with is DL egalitarian. If you're looking at undirected graphs, you just need bounded degree. Yeah. And the topology here is very simple to explain. You have a sequence of rooted graphs that converge. It just means that the way the graph, so these, you think of these as points of view or of a graph. So this is a sequence of graphs as seen from the point of view of some person. The sequence converges if for any finite neighborhood it stabilizes eventually. If I go far enough down the sequence, things stop changing within distance 10 of me in the graph. Okay, so let me give you a proof of this for one particular DL egalitarian graph, and the graph will be the two-dimensional grid. So here everybody has exactly 4 neighbors. I'm assuming that these edges are bidirectional, and therefore it's 4-1 egalitarian. When there's an edge from me to you, there's an edge from you back to me. And degrees are at most 4, so it's egalitarian. And if we just go back for a second to this Benjamini-Schramm topology, if I look at all the rooted graphs, so this is the infinite two-dimensional grid. If I look at all the rooted graph that I can get by choosing the roots in different places, these are really all the same graph. Right? So actually, when I look at all the different rooted graphs that I can get here, it's a singleton. It's already compact. So this is a particular, so here it's particularly easy to see the connection between this and compactness. This is called a transitive graph. Transitive graph is a graph that looks the same thing from the point of view of every vertex. And you can think of graphs that are DL egalitarian as some relaxation of being a transitive graph. Okay, so
Just a small correction to that. In the first bullet point, you don't want to have there exists D because you already have D.
Yes. Yes, absolutely. Thank you. Okay.
It's almost really correct.
I think it's almost surely incorrect. Okay, so we have this two-dimensional grid, which I'll draw schematically like this. And imagine that we also have a symmetric equilibrium. So symmetric equilibrium means that everybody here follows the same rule. Of course, you have to adjust the names of your friends. It's not the same names of friends everywhere, but I think sort of obvious what it means. If you shift the entire graph, you get the same equilibrium. Okay, so what happens here? Everybody converges to the same thing, right? So this is going to be very important. Lim x and t is equal to this x infinity. So everybody converges to the same thing. So in particular, if you choose some vertex n, then for all epsilon, there exists a t such that the probability that x and t is equal to x infinity is larger than 1 minus epsilon. Okay, what am I saying here? Everybody converges to x infinity. So if I look at some particular person, n, and I ask, what is the probability that they've already converged by time 1,000? That's some number. What is the probability they converge by time 1 million? That's going to be closer to 1. This is going to go to 1. If I look at larger and larger times, the probability that they've already converged goes to 1. So for any epsilon that I want, I can choose some large enough time period so that by time t, they're already doing whatever it is everybody will be doing at the end. And maybe for the sake of this proof, we'll do a little bit of cheating, or you can do this in your head, but just imagine that there's some time t where everybody's already converged. Okay? That'll help us remove a layer of epsilons here and deltas. So let's just imagine for a second that the probability that x and t is equal to x infinity is 1. Everybody's already converged by t. It's not exactly true. There's still a chance of 10 to the minus 1 billion that they haven't converged by this time t, but let's just forget about that for a second. So now I want to look at another person, m. And because the equilibrium is symmetric, this is going to hold for the same t for both of them. Right? The rate of convergence is the same thing for everyone because it's the same equilibrium everywhere. And now I'm going to put n and m so far away that the distance, the graph distance between them is greater than 2t. So I'm looking at all the vertices that are t hops away, all the people who are t hops away from n and from m, and these two sets have an empty intersection. They're that far away. Okay? Now, look, what a person does at the first time period only depends on their own signal. What they do at the second time period depends on what their neighbors did at the previous time period, which depends on their private signal. What they do in the third one depends on what their neighbors maybe did. But what I do at a certain time period only depends on the private signals of people of a ball around me of the radius of that time. Okay? So the action x and t only depends on the private signals of people within this ball of radius t around me. Yeah, is that clear? Information hasn't had time to travel to me yet from people who are further away. Now let's condition on theta. Say condition on theta equals 1. So what do we have here? This person has converged by time t. This person has converged by time t. And they've both converged to the same thing, even though they're doing completely independent things, right? Because condition on theta equals 1, the private signals here and here are independent. So I have this random variable, x infinity, or I have these two random variables, x and t and x mt. Something random that I do at time t. These random variables are equal because they're both equal to x infinity, but they're independent, right? How can you have two random variables that are always the same, but they're also independent? Here's a math riddle. What? They're not random. The only way you can have that is if they're fixed. which means that condition on theta equals 1, these, which are equal to x infinity, is fixed. So condition on theta equals to 1, x infinity is fixed. So what are the options? Either it's fixed on 0 or it's fixed on 1. So there are two options here. Either when theta is 1, with probability 1, we all converge to the wrong thing, or with probability 1, we all converge to the correct thing. Well, it's impossible that we all converge to the wrong thing with probability 1. I guess you have to repeat the same thing for theta equals to 0, but it's impossible that we all do the wrong thing because we all have our private signals. We could always just follow that and get a better result than doing the wrong thing with probability 1. So you get that everybody does the correct thing with probability 1. Okay? So I think the magic here is the fact that they agree. Once they agree, they have to agree on the correct thing because they agree before they've even met each other. Okay? How do they agree? That's agreeing to disagree, really. Every pair of agents, this person and this person, cannot converge to different things because they would agree to disagree. And then by induction to the whole graph. Right? If this person converged to a different thing than this person, they would have to be somewhere in the middle, two people who are neighbors and have converged to the wrong thing.
But you're looking only after, I don't want to keep you, but you're looking only after time, some finite time t.
Right, so there's some epsilon, some probability that you didn't converge. So now you have to do a little bit of arguing and you have to say, have to have some limiting statements. So these are only equal with probability epsilon. But it's the same idea of the proof. So you have what this shows you is that x infinity is independent of itself, which means that it's constant. When you put in the epsilon, you have to somehow say, oh, it's epsilon. It's almost independent of itself, but it's epsilon independent for every epsilon. So it's really independent of itself. There's a bit more work to be done, but it's the same idea. Yeah?
Basically don't have the independence, right?
Without compactness?
Compactness, you can't do.
No.
Be sure that they're independent, right?
Well, first of all, once you don't have a symmetric graph and a symmetric equilibrium, then you don't have uniform convergence rates everywhere. And that's where the issue comes in. And really the proof of the general case uses a slightly different idea. But that would have taken more time than I have to explain. Any more questions?
How hard do you think it would be to extend it to more than 2 states?
So this is some of the referees asked us about this. Once you have more than 2 states, there's an issue that it's okay. So imagine that I have just 2 states, but the signals are weak and the prior is so strong that when I see my private signal, I ignore it. Then obviously you're not always going to do the correct thing, right? Once you have 3 states, you have to have some condition on the priors and on the strength of the signal that you have to guarantee that something like that wouldn't happen. But other than that, the same proof would go. Yeah. All right. Okay, thank you very much.